afternoon, everyone. Thank you so much for joining us today for the episode 5 of the Community Connect webinar series. Today's episode is going to be presented by Dr. Nicolas Denans. He obtained his PhD from the University of Strasbourg in France, studying how vertebrates regulate their size and vertebrae number. He then moved on to his first postdoc at Stanford University to study how cells within organs communicate with each other over long distances. Finally, he moved to the Stowers Institute for Medical Research, where he discovered how immune cells control organ generation in zebrafish. At Janelia, Nicolas will use his problem-solving skills and microscopy knowledge to help researchers tackle some of the most challenging questions in biology. Nicolas will be doing a topic for us today on how to select a label for your imaging. And so without further ado, Nicolas.
All right, so let me share. All right. Thank you, Precious, for the invitation and the opportunity to share some of my knowledge that I acquired over a long period of time on how to select a fluorescent label for imaging experiments. So what we're gonna learn today. So first, the basics. What is a fluorophore, and how do we? Oh, sorry.
Sorry, I'm not seeing your share screen on my side.
Oh, you don't?
No, I think it's still me sharing. I'm going to stop and then you share and try again. Oh, there you go.
Okay, so do you see it now?
I see it now. Thank you.
All right. Let's go back. So what I'm gonna talk about today. So the basics, what is a fluorophore and how do we get fluorescence from a fluorophore? Then the choice of your label is most likely dictated by the microscope that is available to you. So you really need to know your microscope before you start designing your labeling experiments. And we're going to see what kind of components you need to know about your microscope. I'm going to teach you how to use FPBase, which is a really great resource to select your fluorophores. Then we're going to switch to live imaging. And so for live imaging, we're going to look at fluorescent protein and chemical dyes, and when to use fluorescent protein, when to use chemical dyes, and which one to use. And I will have a list of recommended choice of fluorescent protein and dyes because there is a lot of them. And there is a lot of hype around some of them. And so it's always hard to have a starting point of which one should we use for my specific experiment. All right, let's start from the beginning. What is a fluorophore? So a fluorophore is a molecule that absorbs light energy and that we emit it as light. And so there is a lot of fluorophore on the market, an overwhelming amount of fluorophore. So they can emit in the UV, blue, green, yellow, orange, red, far red. You have fluorophore that most of you knows because we use them for antibody staining, like the Alexa fluorophores or the Eto fluorophore, the CF fluorophores. But we can also use these fluorophores to do live imaging because we can target them to specific organelles, for instance, and that will be chemical dyes. But we also have fluorescent protein that we can use, and there is also a lot of them. So we have an overwhelming amount of fluorophore available. Chemists have been doing a lot of work over the years. So which one are we going to use for our specific experiments? And that's basically what I'm going to try to tell you about during this lecture. So how do we get fluorescence from a fluorophore? So we're going to start by using a very simplified version of the Jablonski diagram. So your fluorophore contains electrons, and these electrons are going to be in the ground state. Once light targets your fluorophore, it absorbs these lights, the energy of these lights, and it kicks out the electrons from the ground state to this high vibrational state, energy state. Then it relaxes to a lower state, and then very fast goes back to the ground state. And when it goes back to the ground state, that's where it emits photons. So that's what is fluorescence. So that's fluorescence emission. So there is another path that happens sometimes, which is phosphorescence. So instead of going back to your ground state directly, your electron goes to an excited triplet state. And then it goes very slowly back to your ground state by emitting phosphorescence. So phosphorescence is, for instance, maybe some of you had like these watches where you want to see at night, you press a button and you can see light shining, and that's usually phosphorescence. So this happens a lot less than fluorescence emission, but it does happen. So what do we need to know about the property of a fluorophore? And one thing which is very important is called the Stokes shift. So here, what you can see, you have the, let me get you the laser pointer. So you have the wavelength in nanometer and you have the relative intensity. So I told you that your fluorophore is going to absorb light. So this is the peaks of excitation. And it's going to emit light at lower energy, but at a longer wavelength, which is, this is the peak of emission. And so the distance between your absorption peak, your excitation peak, and your emission peak is called the Stokes shift. And so that's critical to know when you decide which fluorescence, which fluorophore to use. And we will I will show that during the live demo of FP-base. All right, what property do we need to know about our fluorophore? So we need to know the extension coefficients. So what's the extension coefficient? Is the potential for a fluorophore to absorb photon at a given wavelength. It's just like how good your fluorophore is to absorbing the photons from the excited light. Then the quantum yield. So the quantum yield is actually the fraction of photon that is absorbed that will give rise to emitted light. So how good is your fluorophore to emit light? And so the brightness, when we hear a lot about brightness, is basically the product of the extension coefficient and the quantum yield. And so when I showed you before, the excited light is going to be a higher energy and the emitted light is going to be at lower energy. So let's put it back in the Jablonski diagram. One thing that I didn't talk to you about is during this transition from this very excited state, which is here, to this state, you have this relaxation phase. And so during this relaxation phase, that's where the electrons are going to dissipate energy. So they can dissipate energy in form of heat, for instance, but also chemically. And that's what produce reactive oxygen species, and reactive oxygen species leads to photochemical damage. And when there is photochemical damage, well, you lose fluorescence permanently. And that is called photobleaching. That's this permanent loss of fluorescence due to this photochemical damage. So what do we want to do for selection of a fluorophore is to decrease photobleaching as much as possible and have a better quantum yield. And the rapport between your quantum yield and your photobleaching is basically your photon budget. And that's what you want to keep as high as possible. So for immunosenic is not very important because all the dyes are extremely bright and extremely photostable. So photostable dye is a dye that resists to photobleaching. But when we talk about live imaging, that's going to be extremely important because the photostability is not as good because you heat the same fluorophore over again over a long period of time. So your photon budget is going to be extremely important. All right. What do we need to know about our microscope to guide the choice of fluorophore that we have? Well, we need to know what kind of light source do we have access to. So do we have lasers? Do we have LED lines? Do we have a mercury bulb? And what kind of wavelengths are available to us to excite our fluorophores? Then we need to know what kind of emission filters we are available. So at which wavelength are we going to be able to collect the light emitted by our fluorophores? And finally, what type of sensor do we have? Do we have specific cameras that have a wide range of sensitivity or lower range of sensitivity? Some cameras are better, for instance, in collecting in the green, and some cameras are better collecting in the red or in the far red. So it really depends on what is available to you. So that's the kind of question you need to ask yourself if you have your own microscope or the microscope manager if it belongs to a core facility. Now that we know what kind of microscope do we have, then we can use FP-base. And so FP-base is a database of a lot of things, fluorophore and spectra viewer. That's what I'm going to show you. It has been made by Tally Lambert's in Harvard, and it's still maintained very highly by Tally. And this is a great resource for you and for everyone. I use it all the time to select your fluorophore. So let's have a live session about it. All right, let's go to FPBase. So I go back. So where you want to go is to go to Tools, Spectra Viewer. And now you can basically enter all the microscope components that you got and to select the best fluorophore possible. So let's say you have a wide field microscope, right? And you want to do a two-color immuno experiment. So you want to have a green and a red, but you don't want to start your immuno before you know exactly which fluorophore is going to be the best for you. So you know your microscope. So you have, let's say, a 475 LEDs for exciting your green, and you have a 555 LEDs to excite your red. All right. So this is your light sources. Now we are going to look for our emission filter. So we have, for instance, a classical FITC emission filter, which is going to be like a 51530. Yes, great. And maybe we can have, yes. And maybe we can have a red, which is going to be a 595, let's say 44. There we go. So we have here our excitation in green, excitation in red, emission in green, emission in red, right? Okay, so, and then let's say we have a camera, which is going to be a, let's say, an Orca flash, whatever. Very fancy camera. So you can see this camera is really good almost everywhere. So this shows you how good your camera, how sensitive a camera is depending on the wavelength. So you can see this camera is pretty good almost everywhere. So let's say we have a good camera. We are lucky. All right. So now, as I said, we want to have a green dye for immunostaining, and we want to have a red dye for immunostaining. So usually immunostaining in the green, it's mostly a 488 dye. So we have, for instance, we can have a Alexa fluor 488. And so you can see this is the excitation peak, which is at 499. And this is the emission peak, which is at 520. So when you look at the excitation peak, it's not really, when we look at our LED, where our LED excites, we're not taking advantage of the full peak of excitation, right? We're still a little bit on the left. In terms of emission, pretty good. We're in a good range. But in terms of excitation, well, it's bright. If your sample is really bright, that's okay. But we're not taking the full advantage of the fluorophore. So let's see if we can find something better. So let's see if we can find, for instance, let's look at a CF dye, a CF 488. All right. Now we have CF 488, which now the peak of excitation is a little bit more on the blue side, on the cyan side, and it's about 490. So now you can see that we can excite a lot better this CF dye compared to the LXA 488. So for a green dye, I would choose, if I have a 475 nanometers LED, I would definitely choose the CF 488 dyes over the Alexa 488, because I will be able to excite closer to the maximum excitation peak. And the collection is basically the same that for the other one. And so the stock shift is very similar between the Alexa 488 and this CF 488. It's just the excitation peak is much closer to our LED. So that's something you can use. Now let's say, okay, so we have our green, we use our CF 488 dye that match our system. Now we want to select the red, and in red there is a lot of dyes. It's not just 488. Like in red, you have a lot of possibility. You have some 546 nanometer, 555 nanometer, 561, 568. There is a lot to choose from. So let's see, because we have a 555 LED, we are going to start with a 555 dye. So maybe we can look at the Alexa Pure What do they have? Alexa fluor, and then what do we have? 555 here. And so if we look at excitation, it's actually pretty good. We are hitting the peak of excitation. In terms of emission, we are a little bit on the right, but we're collecting quite a bright amount of light. So that's actually pretty good. Let's see if we compare it to, for instance, a same Alexa, but we have in the lab, we only have like the 568. You can see like now the excitation is not as good, right? We're not hitting the peak of excitation. In terms of emission, it's still pretty good, but in terms of excitation, we're not as good as the 555. So in this case, I will use the Alexa 555 compared to the Alexa 568. And if we look for CF dyes, which are extremely good dyes from Biotium, what do they have? They have a CF 555. And it's actually looking extremely close to the Alexa fluor 555. So in this case, I will use either the Alexa fluor 555 or the CF 555 is basically the equivalent dyes. So now, okay, so we selected our immunofluorescence. We can use our CF 488 for our secondary antibody for our green, and we can use an Alexa 555 or a CX 555 for our red. So now you can start your immunostaining, and you learn how to do a very good immunostaining from Nihal last time. All right, let's go back to presentation. So now we know how to use FP-base to select our fluorophore based on what we have on the microscope that we have access to. All right, but immunofluorescence is limited, right? We have to chemically fix the sample, so we cannot do live imaging. If we cannot do live imaging, we limit ourselves to what kind of experiment we can do. So we cannot study these dynamic events that occur over time. So we cannot study cell migration, embryonic development, protein shuttling, all this like very exciting process in biology. And so what kind of, if we cannot use this fluorophore, this antibody labeled fluorophore, to do live imaging, which one can we use? Well, we can use fluorescent proteins and chemical dyes. So let's start with fluorescent proteins. So there is a lot of fluorescent protein on the market, like a lot. And it's very, very overwhelming. And there is a new one coming every 2 months. But what they have in common, oops, sorry, let me go back. What they have in common is their structure. So you can see they all have this like barrel-like structure. And inside this structure, which is very common for almost all fluorescent protein, they have a different fluorophore. And that's what makes the property of the fluorescent protein is this fluorophore that is inside this barrel. So you can see between EBFP and EGFP, you have a slight modification of the fluorophore that make it absorb and emit light at different wavelengths. And so what we can do now, we can basically target this fluorescent protein everywhere almost we want. We can label cytoskeleton, for instance. So here in green, you have actin, and in purple, you have myosin. So you can see this, you can follow these ruffles and these phylopodia forming. And you can see contractions of the cells with myosin. We can label cell organelles, for instance. So this is labeled mitochondria with fluorescent protein and lipid droplets. So you can look at the interaction between these two organelles in life and for a very long period of time. So what do we need to know about our fluorescent protein? Well, we need to know the same thing that about any kind of fluorophore. We need to know our extension coefficients. We need to know our quantum yield. And so again, extension coefficients and quantum link product is brightness. And now photo-bleaching is going to be very important because now the photon budget is going to be critical. We are going to hitting our fluorescent protein over and over time with light. So we need to decrease ROS as much as possible, reactive oxygen species as much as possible to keep photo-bleaching as low as possible. And so if you think about it, what do you think is most important, the brightness or the photostability of the fluorescent protein? Well, if you look at the literature, they will tell you brightness, because if you look at any paper where they make new fluorescent protein, they always claim to be the brightest fluorescent protein in the world, right? And so brightness seems to be like something that should be extremely important. Well, I would say if you do live imaging, not so much. There is a lot of hope about brightness. Again, I made the brightest fluorescent protein in the world, and 2 months later, someone else made the brightest fluorescent protein in the world. But it's really not useful if your protein is not photostable. So if your protein photobleach very fast, it can be super bright. Well, you cannot image very long. After two rounds of time lapse, it's gone. So photostability is a lot more important for live imaging than brightness. Also, brightness is measured in a test tube. So it does not correlate with the different cell type environments that you're gonna target your fluorescent protein to. So for instance, you can target your fluorescent protein to the mitochondria, which produce a lot of reactive oxygen species. So that will photobleach your fluorescent protein, and that will affect your brightness. So depending on where you target your fluorescent protein, you will have a lot of difference in measuring brightness. And finally, as I told you, brightness is a product of the extension coefficient, so which is how strongly the protein absorbs light at a given wavelength, and the quantum yield, which is the ratio of photon emitted to photon absorbed. So these parameters are also affected by the cellular environment. So basically what I'm telling you is, yes, we can find data about brightness and photostability, but it's really hard to trust these data because they have been made mostly in a test tube or in an environment that could be completely different from the environment you're going to study. You're going to put your fluorescent protein in. So we can look for some of these data, but there is no really best way to select your fluorescent protein is trial and error. So you can get some ideas by looking at these metrics, but it's going to be trial and error because depending on where you want to target your fluorescent protein and what type of experiments you want to do, is going to be slightly different. So again, we can go back to FP-base and have a different view of it. So this is MST Gold, which is now my favorite green fluorescent protein. This is a complete breakthrough in fluorescent protein development. So this is extremely bright and extremely photostable. I can guarantee that you will kill your cell before you bleach MST Gold. So this is very developed very recently, the past couple of years, and that makes a huge impact in biological science. So what can we find on FP-base? Where you can see your excitation and emission peaks. So you have your spectra that you can use, like we use before for your fluorophore. For antibodies, you can use the exact same thing. And you can see, for instance, your extinction coefficient, your quantum yield, and of course your brightness. Again, extinction coefficient by quantum yield equal brightness. You can see how well your fluorescent protein resists to acidity. And sometimes you have value of photostability. But these values, I'm going to show you, are not very trustful. So let's take two red fluorescent proteins. So we have M-apple in the left and M-scarlet in the right. So we know that M-scarlet is a lot brighter than M-apple. So let's see what FP-base tells us. So FP-base tells us that the brightness of M-apple is 36. The brightness of M-scarlet is 56. So yes, this is actually faithful. M-scarlet is brighter than M-apple. What we also know is M-apple is a lot more photostable than M-scarlet. M-scarlet bleach extremely fast. So when we look at photostability, which doesn't tell us how it has been calculated, how it has been measured, we see a half-time of photostability of 4.8 seconds, which is very short. And here we have 225 and 190, which suggests that M-scarlet is a lot more photostable than M-apple. Well, that is not true. And this is due to the fact that the test that has been made for M-apple and M-scarlet are completely different. And these are the reference of the papers. So in my hand, I can tell you M-apple is a lot more photostable than M-scarlet. So there is, yes, we can look at metrics, and we can look at some metrics, but at the end of the day, to guide us, but at the end of the day, you just need to have knowledge on how your fluorescent protein behave in your particular context. And so there is not a true source of knowledge of this. It's like you need to know a friend who tried it, or you need to try it yourself. It's the word of mouth that's gonna guide you in this case. But I made some recommendation for you today. From all the years I've used fluorescent protein, I made a lot of transgenic animals, cell lines. So I used fluorescent protein quite a bunch for me, and that's only for me. And that's what I recommend to most people here in Janelia too. So for cyan fluorescent protein, I recommend M turquoise 2 and M cerulean. They are fairly bright and decently photostable. Green fluorescent protein, I would still recommend EGFP, mostly because there is a lot of material that you can use with EGFP. So there is a lot of antibody reagents, there is a lot of nanobody reagents, there is a lot of reagents that we can use for GFP to do a lot of different kind of experiments. So it's still a good protein. It's still a bright protein. It's decently photostable protein. M neon green came up a little bit better, and it was like, okay, neon green is like so bright, it's great. And it's true, neon green is bright, but it's not as photostable as GFP. It bleaches a lot faster. So that's something you need to take into consideration when you think about your photon budget. In any case, for green fluorescent protein, as I said, the revolution is M-stay gold. It is extremely bright and extremely photostable. So if you want to have a good green fluorescent protein, M-stay gold should be your #1 choice. Then in orange and red fluorescent protein, there is no M-stay gold version, red M-stay gold version yet. So there is no breakthrough yet. They are not as bright, and they're not as, they can be sometimes as bright or even brighter than green fluorescent protein, but they're not as photostable usually. So my choice are M-apple, M-ruby 3, which is a little bit brighter than M-apple. They have the same kind of photostability, and MK2, which is also very good and photostable red fluorescent protein. So the way I chose this fluorescent protein is to keep my highest photon budget possible. So I want brightness, but I want photostability. So I want to have a good correlation between brightness and photostability. And so that's how I choose my fluorescent protein for live imaging. All right. But why do we want to choose fluorescent protein versus a chemical dyes for live imaging? So what are the cons and the pros of fluorescent protein and chemical dyes? So the cons of fluorescent protein, well, it's labor intensive. So you need to have molecular biology tools and knowledge to generate transgenic materials to express your fluorescent protein in your cells or in your animals. So there is this whole process that is labor intensive and can be expensive. The pros is that your fluorescent protein is going to be constantly expressed. So you can be imaged over a long period of time. Even though you bleach some of your fluorescent protein, a new fluorescent protein is going to be generated. So you can keep imaging and imaging and imaging for sometimes days. For the dyes, the cons are they are not constantly expressed, right? You put your dye in your solution, and then that's it. So you have a definite pool of dye. So this can be depleted fairly fast. So it's more for short-term imaging, and some of these dye can be actually quite expensive. The pros is that you do not require any expensive material and any knowledge in, for instance, molecular biology. You just put it in your solutions with the right concentration and the right tricks. It's not that easy, but you don't need to have so much of knowledge about it. All right, and dyes can be great. So for instance, if you want to study mitochondria dynamics, MitoTracker is a very good dye. And so that's what you see here. You can follow mitochondria over time for fast imaging. And you can also track cells over sometimes a long period of time with dyes such as cell trace here in green, which label the cytoplasm, and drag5, which label the nuclei. So dyes can be a very good tool also for chemical dyes can be very good tools for live imaging. All right. And this is my recommendation choice of dyes. So I made this big list that I will share with you later. In this, it will be probably there's going to be a link for this list. But basically, for instance, if you want to do calcium imaging, I like Cal 520, sorry. So I give you working concentrations. When do you start with? What type of color do you have? So in this case, it's green. I like this dye because it's highly sensitive. So for a dye, it's important. And what's important for a chemical dye is how well it's retained by the cell. When you put a dye inside the cell wants to kick it out. So how well a dye stays inside the cell, the retention of the dye is actually fairly important. What's also important is if the dye is fixable or not, because you might want to do a live imaging experiment, fix your cell, and then do an immunostaining on your cell. So is your dye fixable or not? That's something you need to take into account. If you want to label, for instance, cell membrane, memglow and cell bright are great. As I said, if you want to label mitochondria, mitotracker is pretty good and usually red, far red. So that's where you want to image your mitochondria. You don't want to expose your mitochondria in the green because that would be phototoxic. And the green version of the mitotracker is not great because it actually converts to red when you shine the light on it. So that's not a good option. For these dyes, especially when you want to label organelles, if you can go to far red to limit phototoxicity, choose a far red dye. Then if you want to do, for instance, this dye is great. If you want to label vasculature, so you want to label vasculature in an animal, so you want to inject a dye in the vasculature to label, let's say, brain vasculature. Evans Blue, it's a great dye. It's a great dye because it's extremely cheap. It's probably the most inexpensive dye that you can find. It's really cents on per ml. So it's a very cheap dye and it's a very good dye. So you can, it's a very bright dye. So you can label vasculature using Evans Blue. It binds to serum albumin. So if it will stay mostly in your blood vessel and capillaries, but if there is a break in your capillaries, it will actually leak out. And so that's also great to study retrograde neuronal labeling. And for instance, lectin tomato is pretty good dye to label vasculature, but it's also a very expensive dye. It's like 1,000 times more expensive than Evans Blue. So it depends on what you have access to. Fluorogold is a great dye to image neuronal labeling and very deep. So with 2-photon labeling. So if you want to do like in vivo 2-photon imaging of neurons, that's actually could be a very good choice. So that's basically it for me for today. Thank you so much for joining and listening to this lecture. And I will be happy to take any questions if you have any.
Thank you so much.
Thank you.
I don't know if we have got any questions from the audience.
Don't be shy. I will be here, and I'm happy to help.
If anyone has any questions, please go ahead and put them in the chat box or raise your hand and we will let you unmute yourself.
So yeah, as I was saying, there is a lot of dyes to choose from. It's very overwhelming, and a lot of the time the choice is going to be trial and error. And so there is no, and that's something that we need to think as a community. There is no repository, sorry, of dyes that works best for something, or for some protein that works best for some applications. And that's something I think we need to build at one point, because it's so time expensive to build these new tools and to try these new tools for no reason, because someone already tried them and they know they failed. We do not publish failed experiments. And so you only see what works, but you don't see what's failed. And so I think as a community, we need to think about maybe providing these resources. And so that's what I've been trying to do with this last documents that I will share with you, so you can have access to it. But that's just my experience. And I know that there is a lot of people who tried a lot of dyes and we have different experience with all of these dyes and all these fluorescent proteins. So that would be good at one point to put all of that together to have these kind of resources.
And Nicholas,
Yes.
and I'm just going to jump in and say thank you for that. That was a really, really useful lecture. Even for myself, and I like to think I have quite a lot of experience with dye selection. And I completely agree that one of the challenges is these dyes are often not very cheap. There's a sense that they're not very thermostable, and you don't know if they're going to work for your assay. So I think a community curated database of what works under what conditions and what cell lines is a brilliant idea. So let us know how we can help.
Yes, let's try to think about it.
We've already generated some internal opinions on the DI dyes, for example. So happy to share those with you. They're generally not positive. But yeah, I wondered if you could comment a little bit on your experience of longevity of storage, given the price tag often associated with these sorts of dyes. How you find they keep in storage, if people are going to invest in them, if they work quite well stored in the fridge, or thermostability and that sort of thing.
Yeah, that's actually a big challenge. I always had access to -20, -80, and so for me storage was never an issue. So it's not something I thought about. For instance, when I made this lists, these recommendations, but that's something crucial, right? How the shelf life of your dye is actually fairly important. There's some dyes you use them once and that's it, and you will need to aliquot them and make sure that. And so this should be part of the recommendations too, right? How can we reuse? Can we reuse this dye? How do we store them? And so yes, that's not something I took into account because yes, again, I have been very privileged during my career, and I had access to whatever I needed. But yes, that's something I need to think about. If we need to think about this database, is having another column which is the shelf life of the dye and how can we manage it. So for instance, we have these GF dyes here at Janelia that people can have access for free. You just need to request them and we send it to you. For instance, the shelf life is not very long. We can send them dry and that's perfectly fine. You can keep them. When we resuspend them, usually you need to make aliquots because once you cannot freeze and thaw them, they will die very, very fast. So that's the kind of recommendation that people need to know. And that's not really out there for most people. I didn't even know that. And I work in Janelia. So yes, that's the kind of information that is critical. Most of these dye, they can be sent as dry pellets, which is actually great. Most antibody can be sent at room temperature too. People use -20 for no reason. That's actually fairly stable. When we keep them for a very long time, yes, you want to go to 4 degrees, -20 and everything. But most of these Alexa dyes, for instance, are extremely stable. So yes, that's an extremely good point. Thank you for raising it, and I will think about it, and I will amend the list with this values.
To be clear, that wasn't a critique on your part at all. It's just something that I've been thinking about.
Oh no, that's great. I mean, that's great.
Yeah.
That's a community effort, right? I have thought about some things, but I didn't think about everything. So let's make it as comprehensive as possible for everyone to use. No, that's great.
Sure. Along similar lines, something that I think is interesting that we see is people returning or trying to revisit again some of the older dyes that we've never really thought of specifically. And I'm sorry, I was multitasking a bit. I don't know if you mentioned this in your presentation, but things like Nile Red as sort of like a generic non-specific dye. And those are the nice thing about those, because they're older, they're generally more cost effective, right?
Yes.
So that's something that I think would be interesting to, in a systematic way, maybe revisit and work out where the utility of those sorts of dyes would be.
Yeah, they're still actually fairly useful. And that's the thing, that we're going for more precise dyes sometimes that we don't need. If you just want to label your cell membrane and do some tests, Nile-Red is great.
Yeah.
Nile-Red is a very great dye. Right now, we're going also, we have this, what we call NHS tester that label every single protein. They are not super expensive. And for whatever reason, they're supposed to label every single protein because they are NHS. But depending on the dye, they label specific regions of the cell. And so we can make a full map of the cells with these dyes. And that's maybe something that can be amended also during for another talk, a more maybe advanced talk. Or I can add in the list. I think we should make, maybe we should start to make a list that's that we can update easily and that we can share with people. So we need to think about it. I will need to talk to Liang and see how we can manage that, because that would be very useful. But yes, the old dyes, going back to the old dyes that still work. It's just companies don't want to produce them because they don't make money out of them, because you can make them yourself. So we have here Luke Levis, who is a brilliant chemist and usually take all of these dyes that are out of patent. So we can distribute all these dyes and modify them and distribute them for free. So that's most of the jet dyes come from that.
Yeah, so Luke's work's really great. Thank you so much. I don't want to hog this conversation, so I want to check in if anyone else on the call has any questions or input. I don't see much except thanks in the chat, except for a comment from Mitiat. So Mitiat, you're asking about access to microscopes. So this is a challenge that we're aware of, that across the continent, many of us don't have access to the sorts of microscopes that can actually make use of these dyes. There are a number of initiatives working to address that challenge in terms of making facilities that do exist open access, such as the African Microscopy Initiative, as well as training initiatives. And depending on where you are, please do check out perhaps the ABIC website and map, where we've got the map of existing facilities. We'll be updating that with the survey that's been running recently. Check out the African Microscopy Initiative. They've just closed the most recent call for applications for redistributed microscopes, but maybe keep an eye on what's out there in terms of opportunities to gain access to equipment. Precious, do you want to add anything to that response?
Nothing to add. Thank you, Karen. Yes, like Karen said, please do check out our website, check out our social media platforms. Oftentimes that'll be where we give you the most recent opportunities that are available. We do have an opportunities tab as well on our website, where we put up any funding, things like the peer program from AMI. Those are some resources that you can take advantage of when and if they present themselves. We'll be sure to update you guys. And in regards to the recording for this webinar, it will be uploaded to the YouTube page in about a week, where you guys can access it. And any resources that Nicolas gives us will be included in the description of that YouTube video.
And I wanted to add that the African Bioimaging website is actually great. And if you want to, for instance, I talk about FPBase, you can find FPBase through the African Bioimaging website. If you just go to tools and resources, you will have all these resources. And so that's actually pretty good. You don't have to look at whatever the address I put. You can have access through the website.
Thank you, Nicolas. If we don't have any other questions from the attendees, if there are no further questions, which it doesn't seem like there are any, Nicolas, thank you so much for this insightful presentation. Thank you for your time. Thank you for your time for ensuring that we can learn something important from you today. Here's a question. Shireen, thank you for the presentation and the informative session, Doctor. I have a question. Could photobleaching phenomena be related to the chemical structure of the fluorophore? I mean, the photostability and bleaching are owing to the double bond resonance of the ring.
Oh yes, definitely. It's the fluorophore by itself. The structure of the fluorophore can be impacted by photobleaching, so they can be more or less sensitive to reactive oxygen species. So, for instance, for fluorescent protein, we know that we need to remove cysteines group to make them less photodamaged. So yes, the structure of the fluorophore itself will impact how much the fluorophore is going to be photobleached.
Thank you. Shireen, do you have any other questions, or does anyone else have any other questions? Feel free to also raise your hand. You can ask your questions directly to Dr. Nicolas verbally if you'd like, if you don't want to type them out. Okay, Shireen seems good. And if nobody else has any other questions, I think that'll be all for today. Again, Nicolas, thank you so much for this presentation. We hope we can continue to hear from you, your expertise in the future, and hope we can partner on other opportunities. Thank you all for attending as well. Keep up with our social media pages. We will continue to have more episodes of this webinar series, so do keep your eye peeled on our website and our different social media platforms. Thank you so much for your time today, everyone. Enjoy the rest of your afternoon.
Right, bye everyone.
Thank you.
Thanks, Nicolas. Thanks, everyone. Bye.